All right, these two chapters here are really one big chapter, sort of like the way the last two chapters were all about the electrons and where they were and the orbitals. Um, you could present them as one big long one, but they're kind of they just cut them in half. All right, let me go full screen. Sorry, getting lots of pop-ups. Protect your computer, etc. Okay, so these two are all about chemical bonding. And chemical bonding is all about electrons, which is why we needed the previous two chapters. All right, so basically it explains how and why the atoms connect. So we had chemical formulas, some that you're familiar with, for example, like water, it's H2O, and hydrogen peroxide that you use to clean cuts is H2O2. And the first theory, as usual, not a history class, but for those that have to take bio, all organic bio majors, so you have to take OChem, all organic chemistry is based on Lewis theory, and it's just, his last name. And this theory comes from valence electrons. Remember, the valence electrons are s and p orbitals. So the way we use this theory to draw up what the molecules look like. And so they're called Lewis structures. And this allows you to predict the way molecules are going to behave. And now, people, chemists know how they're going to behave, but as you're learning it, you can use these, the valence electrons, and via this model, put them together and predict and know how different molecules are going to behave. Right now, depends on the book. I don't know where this electron dot came from. I never heard of it until the last 10 or 20 years or something, and seen it in books. It's always been called Lewis, but it means the same thing. And then we'll see how through these two chapters, this is going to tell us what the shape of the molecules is like. It obviously then, if you know the shape, predicts the size, and then what we haven't learned yet, polarity. And polarity is just basically the magnetic behavior, the uneven distribution of electrons. All right, so why do atoms bond? It's basically because it's lower in energy. The atoms themselves are happier when they come together and move their electrons around to be less reactive. And things that are stable don't change. It's kind of like, if you throw a marble into a bowl, right? Gravity's pulling it down and it rolls around in the bowl or until it gets to the bottom. And so molecules, chemical formulas that have the most stable, happiest formation are then the lowest in energy. And that's what most molecules are headed towards, as being something stable. So things that are higher in potential energy are things like gasoline, right? And you can burn it and release the energy. And the things that come out the tailpipe of a car, for example, are lower in energy. It's carbon dioxide and water, right? And you don't ever see water catch on fire, etc. So we're going to start putting, via these orbitals and the valence electrons, put these together and come up with the structure, shapes, and then eventually that polarity. All right. So the potential energy between remember that the protons are positively charged, and we'll see this distance, which we covered last time, the radius, and think of it as potential energy between the charges, and we'll see how these distances relate to those charges. So on the left is the technical formula, but we're not gonna, solve all of that. What we really care about is just the behavior, the potential energy where Q1 and 2 is the charge. And so these would be the charges on the ions, +1, +2, +3. So it's inversely related to the distance. So the charges times one another divided by R. We don't really need to calculate it. We're just going to look at relative relationships between them. All right, the E is a constant, but again, we're not going to use the equation on the left. It's overkill. Charges with the same sign, they're plus, and the magnitude gets less positive, the charges get further away. For charges with opposite signs, it's negative. So kind of like just like the way exo and endothermic was. Exothermic was negative. If you're around a campfire, the heat came off, right? So that wants to happen. Opposite charges attract each other. So the negative is favorable. Like charges is like an uphill endothermic reaction. They don't like each other, right? Things of the same charge actually repel each other. So the more negative the potential energy, the more stable the system, or in this case, it'll be, the chemical formula. So, back to the idea of like a marble, you throw it into a bowl. The marble is the least negative and most stable when it's at the bottom of a bowl, or like you throw a rock, or again, let's say a round ball into a swimming pool. It makes its way to the bottom. Same thing here with these chemicals. So here's just sort of a picture, right? Same charge, whether it's positive or negative, they repel each other. So they don't want to be super close to one another, and they're happier further away. The like charges, they're actually, they attract each other. So they actually want to be near one another. And the closer they get, the more energy is released and the more favorable, right? So lower in potential energy is favorable, higher up is unfavorable. So these different bonds, and we'll talk about the different ones, we haven't categorized them yet, but a chemical bond is when the potential energy of the bonded atoms is less than the potential energy of them separate, right? So these valence electrons, the configurations and everything we were doing before were just for the single atoms. And except for the noble gases, you don't have single atoms, right? All the chemical formulas you've seen are at least 2, 3, 4, right? And then, you'll get into organic chemistry and biochemistry and see, all the different molecules, vitamin C, nicotine, et cetera, et cetera. All right, so for these small systems, what we're first going to look at is the different electronic things going on. So again, protons and the nucleus. The nucleus is, they can't be in the same location. They repel each other. So there's some distance that the nucleuses push each other away. The nuclei push each other away. The electrons don't want to be with each other, but the electrons are moving. So, and they're in those orbitals. So that's a little more complex. We'll kind of come back to that. And then there's the protons and the neutrons, and they are attracted to one another. All right, so there's 2 types of bonds. Well, 3 really, but you'll see the majority of it is spent on these 2. So this is sort of good categorization and what's most important, and you see that by how much time we spend on it. Ionic is where the electrons have been transferred, and this is pretty simple. We already did this with the moving the charges and naming and whatnot back in chapter 4. We'll spend just a little bit of time on it because it's pretty simple. The metals lose the electrons, they go to the non-metals. Ionic things like table salt are really stable. And so the story's kind of over there. The electrons have moved, and that's that. Covalent, and sometimes called molecular, but covalent is the specific type of bond. This is the world of organic chemistry. These are non-metal atoms, which there's not a lot of compared to the metals. And carbon is the most variable and dynamic of those, and that's why you can spend years and years and an entire lifetime studying organic chemistry, and lots of people too. But you see this in your academic life, that there's a whole year devoted to learning organic chemistry. And this is where the electrons are shared, and those s and p orbitals that you learned about are going to be very important. Metallic is even less than ionic, right? This is really more for engineers, and electricians and physicists. We'll cover it a little bit, and we're going to care about it because all scientists use things that have metal in them and electricity and stuff and whatnot. And thinking about it in the electronic nature, a piece of metal is like a giant, huge number of electrons, and they're all together. And you know that metals can conduct electricity, and the way they do that is by having the electrons freely move throughout the whole piece of metal, and that's why metals conduct electricity. So in covalent, they're shared between just the chemical formula. Ionic, the electrons have gone from one to the other, and then in metallic, they're uniform and can move freely throughout the piece of metal. Okay, so as usual, here we have on the left of each picture is the thing you kind of knew and were used to before you started taking freshman chemistry, and then on the right is the way what we're trying to learn here, right? The atomic level. So, on the top one here on the left, the table salt, this is a pretty big chunk, or they've really zoomed in on it. But if you look small enough at table salt, it does look like it's very crystalline like this. And we won't dive into the packing too much. We'll brush up against it. But it's plus and minus 1 electron is moved between them. This is how you find it in nature. You don't find chunks of sodium or chlorine gas, which we kind of talked about last chapter. All right, then ice, you've all seen, touched, had ice around, and this is, it's H2O, and this is what we see on the atomic level, is this regular repeating array. And these little pockets in here, and we'll see why coming up, are what makes ice float, is there's this little bit of volume. And then this is the way you want to think about a piece of metal, is it's just one atom after another. They each have their valence electrons. So sodium, for example, has 1 electron. And when you have conducting electricity, if an electron moves off one atom, the atom next to it, that electron just jumps in its spot, and it's sort of like an elaborate game of dominoes. Okay, let me grab my water real quick. All right. Okay, so again, ionic metals and nonmetals. The metal's been the electrons been transferred from the metal to the nonmetal. We looked at the ionization and electron affinities, ionization energy, and followed those trends. So you can actually calculate the masses of these, and we'll come back to ionic, but it's sort of the shorter story. Covalent's the one that's much more complex, and there are many, many more examples. Again, the whole world, the whole year of organic chemistry. Right, so they have high ionization energy, so the electron's difficult to remove, and it's not going to leave the atom. Thus, it's an insulator, and it doesn't conduct electricity. So these nonmetals, when they come together, it's better for them, and that's why they exist this way, is to share the electrons. Again, that's, lower in energy, more potential energy given when they interact with one another. So how do they share them? They share them like you see down here, right? The 2 protons have this optimum distance between each other, because the protons, the nucleus, they repel each other, so they can't be right on top of one another. And then the happy way to do this is to have these electrons that are negatively charged in between them, and then there becomes this happy distance, and that's that radius we saw last chapter. Right? And this is just showing you, on the left and the right are 2 examples where those are higher in energy, and so the one we see in the middle is the favorable one, and that's how these things come together and exist. All right, so remember what valence, how we count up and where the valence electrons come from, comes from the S and the P blocks, right? So group 1, group 2, and then group 3 over to group 8, right? So 1, 2, 3, 4, 5 all the way across. We'll see lithium and beryllium very, in small amounts, and boron on occasion. You'll see that in OChem, but really our focus is going to be from carbon over, and the other nonmetals below carbon to fluorine, right? And there's really not much story to tell with the noble gases because they are very unreactive. This little thing here, transition elements all have 2 valence electrons, and that's because the D block is in between group 2 and group 3. So all the transition elements have those 2 s electrons. And this is why one of the common reasons most transition metals like to be in a 2+ charge state. All right, so Lewis structure, or if you see it somewhere, electron, I'll never write or say electron dot. But basically the way this works is think about the orbitals if you made a box around the element, and then you put those dots in. So the first 2 electrons, lithium, beryllium, go into the S that's there, 1s, 2s, I mean, and then now you start filling them in just like you would around the P in those electron configurations. So this Lewis dot is basically the same as those electron configuration and orbital diagrams, the boxes, except now the line where the electrons go is around the element, and instead of little arrows up and down, it's dots. And so every Lewis dot is going to look just like the ones you see here for the elements that are below these ones. And we really won't use the lithium and beryllium ones. This is for covalent stuff, which is mostly going to be carbon to fluorine and the elements below it. All right, so for ionic compounds, it's pretty simple, right? Lithium, for example, same as sodium or every other element, potassium on down below it. Lithium, the metal, will have the 1 electron. Lithium, the ion, or group 1, the ion, is going to be missing that electron. Then, for example, group 7 and everything below fluorine, right? Fluorine, chlorine, bromine, etc. It has 7. It wants 1 more. The 1 from group 1 goes to it, and now it has 8 around it, which gives it the configuration same as a noble gas, and this is much more stable than the single unpaired electron element. Right? Unpaired electrons are reactive, and we'll see why as we go along, but good to note just ahead of time as of now. Okay, so basically what we're looking at is our old electron configurations. Right? And we saw and already knew this, metals lose the electrons, they become cations, they move to that noble gas. Nonmetals do the same, except they gain the electrons and again go to the noble gas configuration. So this one, it picked neon. Right? Neon becomes the core, and then you lose these outermost electrons. The metals do to get the same configuration, and the ions then are much more stable than the elements on their own. And then the nonmetals do the same thing as well. So it left neon out, right? These sodium, magnesium, aluminum are the elements after neon. Argon and fluorine are the elements before it, so they're gaining the electron, but they all have the same noble gas. Noble gases are unreactive, and that's why these ions are much more stable than the individual atoms. And you don't see these.
Jade, join the meeting.
Interesting. A little announcing there, but I thought I had that off. Anyway, all right, so you can tell then that the S plus the P are the electrons that make up the valence. There's 2 in the S, there's 6 in the P. That makes 8 total. And so the rule that goes by from these Lewis dot structures is called the octet rule. Oct meaning 8. So everything wants to have this noble gas configuration. N generically, whatever row, doesn't matter. And there's a few exceptions to this, and notice there are those high elements before you get to carbon. So you might see one or two of these. I tend not to put these on a test because they're exceptions to the rule. And I think you've seen over the course of the semester, my focus, our focus, is the general trends and preparing you for the next class, not testing people on who can remember these strange and unique exceptions to the rules and to the general trends of things. Okay, expanded octet, right? To expand something means beyond it. This applies for elements in the third row, third period, or below. And basically what it is it's that picture that we saw a ways back, where the orbitals were staggered in their energy. And these elements in the third row and on, they can reach these d orbitals that are similar in energy. So electrons always go to orbitals. If they're going to move, they can move into orbitals of close in energy. And so we'll see some expansion, which isn't terribly important, but it's not a rare exception. So the exceptions up here are just, helium's a noble gas. You're not really going to do much with it. Lithium and beryllium are metals, and beryllium doesn't get used much. Boron is a decent exception for OChem. So these ones we won't really use too much. And hydrogen is really simple. It has one electron and makes one bond. It has a few rare exceptions in its behavior, but beyond the scope of our class. But this expanded octet, it's a more common exception. So we'll see the expanded octet. That'll be on the exam, but these lithium, beryllium, and boron ones will not. All right, so the basic idea here is that you take these electrons and arrange them around the atom and make it more stable. That's called the octet rule. The more stable the way the electrons are oriented, the lower in potential energy, and the more often you will see that molecule as drawn using this methodology. Okay, ionic compounds. So again, this is a bit short when it's ionic because there's not much to tell. Hard, brittle, and crystal solids. Usually salt, when you've seen it, the particles are so small, they're like grains of sand. So it's hard to relate to that. But if that's just relative to our size, if you used a microscope and you had some tweezers, you could take them and you would see that they break apart like kind of like icicles. If you've ever seen, been somewhere cold and grabbed an icicle off a car or like a roof ledge or railing or something, and they're much like that and break apart. Or like a lollipop, if you hit it with a hammer, like rock like candy. They're kind of similar like that. These melting points are really high. So 300 C is, I don't even know what that is Fahrenheit wise. Boiling water is 100. That's 212 Fahrenheit. So, I don't know, 500, 600, 700, 800 Fahrenheit, something like that. Which means you can't melt these at home, right? Versus covalent stuff comes in solid, liquid, gas. So all these ionic things are, the electrons transferred, they're really stable and they're much different in their behavior. In the liquid, it conducts electricity. We'll come back to that, not terribly important here. And then soluble in water, I assume everyone's been in the ocean, right? And it's salty. Okay, and so the reason that these boiling points of ionic compounds are so high is they're like tiny little magnets that are right next to each other, and it's uniform throughout the network. And so it takes a lot of energy to break the attraction between the anion and the cation. And so melting it is very difficult. The conductivity here, this is a classic way. You might do this in Chem 162, right? Here's the solid thrown in. if you pour water in there, right, you can't tell the difference when you look at salt water or fresh water, what's in there. One of the dangers in life, right, is that water can be contaminated and things like hazardous heavy metals that do damage will dissolve in there and you can't see them with your eye, right? And you have to do testing. This is just a little circuit and you can see the light bulb lighting up. It won't last forever. What'll happen is one electrode is positive, one's negative, and the opposite charged ions are gonna flow towards that electrode. And once they've completely once you've used all the ions in solution, the light will dim out. So it's like a little battery. And we'll dive into this in Chem 162, right? And so here's just a blown up picture where the ions are moving towards the oppositely charged electrode. All right, so we're going to use these Lewis symbols for both, but we'll see that the ionic one is pretty easy. And if you're a bio major, you're going to have to take OChem. This is the way organic professors like this to be done. You always draw this arrow of where the electron is going from where the electron is to where it's going to go. So this electron goes here, and then this is what the product looks like. If you don't have to take OChem, not a big deal. If you do have to take OChem, this is the way they do it, and they love it, and it's got to be this way. And you don't draw it the other way. That's incorrect. All right, so the electrons transfer until the metal loses all of its valence, the nonmetal, and gets to that octet, whatever it is. The number of atoms are adjusted to the electron transfer, and that becomes even and cancels each other. And we already did this, right? So lithium plus whatever it was, fluorine on the last one, turns into lithium fluoride. Now it's lithium and we're doing oxygen. Oxygen needs 2, so we're going to need 2 lithiums, right? We already did this, so it's a rehash, right? It's simple integer math to cancel the charges. So lithium has a +1, oxygen wants to be -2, so we need 2 lithiums. All right, so all this is going to do is talk about the energies we covered last chapter and now apply it to our chemical bonding, right? So the ionization energy is that energy to get rid of the electron, remove the electron from sodium. The electron affinity is where the chlorine gains an electron. And so the combined values of these gives us the total energy to heat to form these things. So the one thing here is that remember that chlorine shows up as Cl2. So really we need 1/2 of it because the product is just sodium chloride. It's not 2 of them. Right. The chemical formula, remember we saw these pictures. It's this never ending on the atomic level pairs of electrons. But all we report is the empirical formula. That's that simplest ratio, 1 to 1, 1 to 2, 1 to 3, 2 to 3, that type of thing. These ionic compounds arrange in something called a crystal lattice. And this is where, every cation is surrounded by anions and vice versa. And that maximizes the plus and minus charge. Right, and that when it comes together in this lattice, the energy that you get from this is called the lattice energy. Again, like we saw in the electron affinity and ionization energy, everything was from the gas phase. But when these things come together, it's more favorable than the individual atoms. You don't find the individual atoms in nature, right? Table salt's in the ocean and it's happy with the noble gas configuration. So these things are, and that's why this is always exothermic when you combine these two, because they don't the individual atoms don't have that electron count, and they want to have the noble gas electron count. So this lattice energy then is going to vary, like we saw in the beginning with the charges. It's going to vary depending on the distance, the R, the size of the element, and then the charges between these two. Haber, this is, again, not a history class, two famous, really, physicists. And Hess's law is where we added reactions together and then added the heats together. So you can basically go and find the heat, say, of table salt by doing, the ionization energy, the electron affinity, and the energy for each thing. And that's what you see down here. I'm not going to put one of these on the test. It seems, a little much to me, but, here's the individual atoms. We always know that this is going to be exothermic, right? To remove electrons takes energy. And here, you got to split apart the two chlorine atoms together, that's covalent. We haven't gotten to that yet. Then, there's the ionization. So formation, here they're a solid, you got to make them a gas, right? Then you got to split the chlorine, and then you got to strip the electron. Then the chlorine gets the electron, and then these two magnets, if you will, positive and negative, come together, and you get a huge energy back if you're doing this step by step. But the important thing is the HF formation for these ionic things is exothermic. The purple, lighter, or I guess darker purple, not magenta, is always exothermic. It's favorable. And that's why whenever table salt was formed on Earth, it's in the ocean, and it's not going anywhere. So this just walks you through an example. Again, I'm not going to put one of these on the test. It's not that critical, I don't think, anyway. You might see this again in an engineering class, but again, I know majority of the class is going to move on and, take 162, but you're going to take OChem at some point. And this is not critical to OChem. And it's really just a bookkeeping. And I felt like we did Hess's law with chemical reactions, which is more important, especially for people going on to take OChem. So you just keep track, bookkeeping, and add all these up, and you can find that lattice energy. To me, what's more important is using that equation we saw in the beginning of the charges, and then inverse means, right, divided by the distance. So that's the R, the radius. Larger ions mean center of positive charge, so bigger cation is further away from the negatively charged electrons. That's a longer radius. Larger ion means weaker attraction because you're dividing it by R, and R is bigger, so you get smaller lattice energy. And this is just showing you the trends that we already know, or that they've already told us by the 1 over the R. So for here, the chlorine is all the same. Right, we're just in group 1 and we're moving down. So the radius is going to get smaller. And that means that this positive, cation, think of it as a magnet, is coming together with the same chlorine, and it can't get as close. So because the layers and the distance of the electrons, those core electrons, protect it. It's sort of like, if you stuck two magnets together, but then you put, a towel in between them, and they don't get to go as close to one another. And so the attraction isn't as strong, right? Like, think about putting a magnet on a refrigerator. It can hold a piece of paper up there, but it can't hold an entire book. So the closer two magnets are to one another, the stronger the interaction. So that's the R in that formula. Then the other thing is the charge, right? So again, think about a magnet on your refrigerator. The larger the magnet is, and that would be the larger the charge, the stronger the interaction. And so the lattice energy would be the equivalent of how strong a magnet is, right? And so here, sodium and fluoride and calcium and oxygen are basically the same size, right? These are picometers, and they're pretty close, 231 versus 239. But the energy is much greater for the calcium oxide, and that's because the charge is twice what the sodium fluoride is. And so it's not perfect, right? 9 times 4 would be 36, and this has gone from 900 to 3400. But this is that squared factor to the charge, right? 2 squared is 2, and again, 2 squared is 2, so it should be, from that generic equation, it should be 4 times bigger, and that's pretty close to what it is. All right, so an example would be, think about, the lattice energy and compare these. So what makes them different? Here's all their locations on the periodic table and their different charges. So we've got some +1 and +2. Obviously, the things that are both +1 are going to be lower. The +2 are going to be higher by about a factor of 4. We saw that on the last slide. So we can separate each groupings of 2. And then it's just the size. So you look for the smaller radius, and that's going to give you a bigger difference. So that helps us orient 2. And then same thing here where it's the distance, and that helps us orient and rank the other 2. All right, so this was kind of typical all semester long, sort of the things you already knew before you took the class, and then what information you want to walk away with on the atomic level. So ionic compounds have high melting points and boiling points. Not that you've probably tried, but you can't melt or boil sodium table salt at home, right? If you want to try it, you can, turn on the stove and put a pan in there and turn it up as high as you want, and you can throw some salt in there. It's not going to melt. And now the black bullet here, the reason for that is this crystal energy. It's the charge on the ions, the sodium and the chloride, that lattice energy that comes together, and the way it's like a couple little magnets, and they like each other so much, it takes more energy than you can come up with in your kitchen to melt. Again, they're brittle, but most salt is like table salt is the most common way, and it's so small they look like grains of salt. But if you had a magnifying glass, you would see they're kind of like icicles. So what makes them so brittle and fracture apart is when you put some pressure. If you can imagine yourself taking a hammer, or a chisel, and like hitting a big salt crystal. This is where it's happy. Then when you put some pressure on it, it fractures apart, because as it slides, all these lined up charges then go from what they like to what they don't like. So as soon as there's enough pressure to push them towards the charges they don't like, this is where the fracture happens. And so the macroscopic thing that you see is that it's brittle, right? You push on it and then it just breaks apart. Ionic compounds conduct electricity in the liquid state or when dissolved in water. I wouldn't say that you really knew that beforehand. But you'll see this again, and it won't be on the test, but you'll see that again in Chem 162 when we look at how batteries work. And then 2 is, in theory, if you knew the red bullet, and again, this is really foreshadowing for Chem 162, is those ions moving, flowing through. They go towards the opposite electrode. And this is only possible if they can move past one another. In just a pure solid state, they can't do that. Okay, so all right there, that this is the break R end, and that's pretty much ionic compounds and end of story for the most part. And so the rest of these 2 chapters is all going to focus on covalent bonding, and the majority of what will be on the exam and is basically what you need to know for week 1 in organic chemistry. The orientation and the lineup of these things aren't the best so for those of you, and I know a fair amount are bio, you're going to take organic chemistry, and the end half of this chapter and the whole next chapter is basically what they'll review really quickly the first week of organic chemistry, and then you'll build off it just focused on carbon. All right, so covalent means nonmetals. They're sharing 2 electrons, make 1 bond. An atom may have more than 1 single bond. We'll see that coming up why. But let's start with a pretty easy example. So our Lewis dot for a fluorine atom looks like this, right? S and P, it has 7, it wants 8. If you push these 2 together, then they share that 1 electron, right? And now instead of each fluorine feeling like it has 7, it's tricked into thinking that each one has 8. And then whenever there's electrons in between 2 atoms, we represent that with a bond by drawing a dash or a bar or whatever you want to call it, and connecting the 2. So there's our single bond, 2 electrons in between an atom, 2 atoms. All right, let's, a little more complicated a touch. Let's talk about water, H2O. So oxygen has 6 electrons. It wants 8. Hydrogen has 1, and now the exception is hydrogen doesn't want 8 electrons. It only has 1 orbital, the 1s orbital. So hydrogen wants 2 electrons. Same concept though, you push them together. Now the whole molecule has 8 electrons. Each hydrogen thinks it has 2, and the oxygen thinks it has 8 because they're sharing them. 2 electrons in between 2 atoms, we draw a bond, and this is what water looks like. So what about if you have more electrons? Here's the Lewis structure for oxygen. And each oxygen atom has 6, so a total of 12. If we push them together and we put 4 electrons in between each atom, oxygen atom, then the other 4 on the outside, then each oxygen atom thinks it has 8, sharing the 4 between it. If you have 2 electrons, you make a single bond. I think you can see where this is going. If you have 4 electrons between 2 atoms, then it's a double bond. Likewise, so 2 atoms sharing 2 pairs of electrons, so 4 total, gives us a double bond. Now guess where this is headed? If you have 3 pairs of electrons or 6 total electrons between 2 atoms, it's called a triple bond. So the Lewis structure here for nitrogen has 5 electrons, a total of 10. The only way for each nitrogen to feel like it has 8 is to push it together. You put 6 in between, and then they each have 2 on the outside. Now we have what we call a triple bond, and each nitrogen thinks it has 8 electrons. All right, so we've taken those valence electrons from the s and p orbitals, and those s and p orbitals become more important later. This allows us to then put the molecules together by trying to give every atom 8 electrons, the octet rule. It tells us what combinations are going to be stable, thus exist, and which other ones are not likely. We want that octet, with the exception of hydrogen, that just wants 2 electrons. And so you can predict the way chemical formulas and these molecules behave. And we're getting to the directional, what that means. So this is a little foreshadowing. The shared electrons are most stable between the bonding atoms, and that gives us the bonds. And then we get these individual molecules like H2O instead of table salt, which is, 1 mole is 6.022 times 10 to the 23rd. The ionic compounds are this three-dimensional, on the atomic level, like never-ending, alternating array of positive, negative ions, cation, anion, cation, anion. Instead, we get concrete small molecules like water, H2O. All right, so like before, the top bullet in red is the thing you knew before taking chemistry, and then on bottom is the black um, that you're walking away with now, having learned and studying chemistry. So molecular compounds have low melting points and boiling points. Sure, we breathe gases. You've seen water as ice, liquid water, and then steam, food, all kinds of things. Melting and boiling involve breaking the attractions between the molecules, but not the bonds between the atoms. So what it means to boil water, for example, is the individual water molecules are moving much further away from one another. But the water molecules don't, the bonds within them don't break. So the formula doesn't change, right? Water is H2O, whether it's ice, frozen, liquid water moving, sliding past one another, or steam, where the molecules are much further away, but the covalent bond of hydrogen and oxygen bound to one another, that doesn't change. Those are much stronger. And breaking those is organic chemistry. The attractions between the molecules are fairly weak, and that's why you can boil water and you can't melt or boil table salt. We'll get to the polarity, we're not there yet. So this is a foreshadowing bullet down here. All right, so this is showing gasoline or an additive of it, one that has 5 carbons, 12 hydrogens on it. And you've been to the gas station before and you can smell gas. Or if you've been in a garage and used turpentine or nail polish remover, these are similar types of molecules. And it's much easier if you've ever spilled gasoline on the ground at the gas station. It evaporates and disappears into the gas phase much faster because the boiling point is much lower. So just like water, you have a bunch of molecules here in the liquid phase, and they do like each other. That's these dashed lines. But the covalent bonds that make up the entire molecular chemical formula, those don't break. The little interactions between them, that's what breaks and makes it go to the next higher phase, right? So here, the molecules that are in the gas phase, they're still C5H12. The covalent carbon-hydrogen bonds have not broken. It's just these little dashed lines, the interactions between them, that have been broken, and then now they can be in the gas phase. Molecular solids, some, like they're all kind of different, that are solids are brittle and hard, but can be soft and waxy. So, a piece of toast versus butter, right? There's a lot of different covalent compounds can take on lots of different forms, from solid, gas to liquid, and it's due to the size and the number of bonds and the forces between them. So we'll see that the chemical formula doesn't take, again, the covalent bonds, the chemical formula stays intact. However, it's the polarity. So the elements have different degrees in which they like electrons, something called electronegativity we'll get to. And those can be different throughout these covalent compounds. But it's the little intermolecular, right? The interactions between those dashed lines. So this dashed line here, this varies from compound to compound. And so this is why gasoline versus water versus motor oil have different boiling points, or something like syrup, right? If you put like syrup on your pancakes, you'll you'll have a tough time boiling syrup on the stove at home, but you can boil water. And in Chem 162, that's what it starts off when you start to look at those little dashed lines are the attractions and what makes them the way they are. Molecular compounds don't conduct heat or electricity. We'll get to acids coming up and see that they do. But you use a pot holder, right? You don't use, metal can conduct heat and electricity, right? You don't stick your keys in a electrical socket, you'll get electrocuted. And same thing with heat and electricity, right? When you pull a pan out of the oven, you go and get something that's non-metal, that's made up of non-metal covalent bonded molecules like an oven mitt. Right, and this has to do with there's no charged particles, there's no ions to flow back and forth, there's no metals in there. Okay, so bond polarity, what does that mean? What it means is that these covalent bonds that we could draw and put together by these Lewis dot structures, they're not all equal. There's some unevenness to it. So as we initially drew it here before, when you have any two nonmetals and you have electrons in between them, you form a bond. But the bonds, the sharing isn't perfectly equal. There's going to be some elements that pull the electrons closer to it and some that do not. So basically what we get is we have a polarity to it. We have one end that has more electrons, spins more. The electrons, remember, are moving in those s&p orbitals, but they spend more time near one element than the other. So one end of the bond has a partial positive, the other one has a partial negative. All right, the most extreme example of that is hydrogen and fluorine. So hydrogen has one electron, fluorine has 7. If we push them together, we have 3 pairs, so 6 electrons that are not forming a bond, and then the 2 electrons in between them form a single bond. Well, it turns out En stands for electronegativity. It turns out fluorine is the most electron loving. It has the highest electronegativity number of the nonmetals, and hydrogen has the lowest. So you can measure these, but we won't need the actual values for bio people and for OChem people, but more bio. This is typically how a lot of models of molecules are represented. And down here below this one is, a lower, less, techy. So this one up in the right is more high-tech way, where you're showing that the atom on the right, fluorine, is much bigger and the electrons spend more time around it. Then the way you can show the charge is put a little plus sign next to the element that has the lower electronegativity number, a little minus sign next to the element that has the higher number, and then connect the two and put an arrow. This tells us, when you see this in the future, this tells you that this bond is not perfectly even, and that the hydrogen is partially positively charged, which the hydrogen essentially always will be, because it is the least electronegative of all the nonmetals, and fluorine is the most electronegative. All right, this little symbol here is the symbol for showing a partial charge. So whenever you see this, I forget the name of it. I'm sure it's got some Latin name. I'd have to look into Word under symbols and look it up, or Google it out. But anyway, it just means a partial charge. So the hydrogen has a partial positive charge and the fluorine has a partial negative. It's not like the ionic compounds where the electron completely left one element and went to the other. Right? They're still sharing the electrons, the hydrogen and the fluorine, but they're not doing it evenly. The electrons are spending more time closer to the fluorine. Right, one of the ways that you can observe this, and this is basically how a microwave works, is you take and create an electric field. And this is what a microwave does, is it takes an electric field and then it oscillates it back and forth. And what you have is the molecules will flip to orient, and they'll put their negative end towards the positive plate, their positive end towards the negative plate. And so if you can flip the charge of the plates, what you get is you get the molecule flipping back and forth. And that's the equivalent of, say, friction, right? If you've ever been cold, you rub your hands together real rigorously, and that creates heat, the friction. And so that's how a microwave warms up your food, is it takes the water molecules in it and it has them flip back and forth, and basically it vibrates your food from the inside out. So if you've used a microwave a fair amount, right, one of the ways to heat up your food quicker is, if it's really dry, is to put a little bit of water in there. Or say rice that's gone kind of dry, if you put some water in the bottom and put a lid on, it'll steam it back to life. And that's how it creates the energy. It's not, my mom thinks it's magic, but it's not magic. It's just an oscillating magnetic field to a little polar molecule called water. All right, so electronegativity is this measurement and a degree of how much an atom likes electrons and pulls them towards it in these covalent compounds. So increases across the period, decreases as it goes down. So there's this general trend, and really we only care about the nonmetals, which isn't that many elements. And it doesn't apply to the noble gases, so that complete group is off the table. So it's really about how close are you to fluorine. So the bigger the difference, the more polar the bond, and we saw the extreme of that, hydrogen and fluorine. And the negative end is the one that is more electronegative. It pulls, right? The electrons are negatively charged, so it pulls the electrons towards it. So again, hydrogen's the lowest, right? Lithium on over, all these are metals in here. So we really don't care about the metal values. It's not really that big a deal. What we care about is carbon over to fluorine and the elements below it. That's the world of organic chemistry. Boron a little bit too, but you really won't see that much until you get to OChem. So what we care about is hydrogen, and then carbon, nitrogen, oxygen, fluorine. And then you won't use silicon much because it's a metalloid, right? And these elements are metalloids and then become metals. So what we really care about is an over one. We'll use phosphorus, sulfur, and chlorine a bit. Arsenic is a metalloid, so we won't use it much. So then over to selenium. So really, we're just talking about sort of a little triangle of elements here. Only 6 or 7 elements, really. But general trend, right? As you go closer to fluorine, which is to the right, and then up. And you can see the numbers on here. You don't need to have the numbers memorized, but you do want to know the trend. All right, and here's why we don't need to measure and know the actual values, is there's these lines in the sand. So if the difference is 0, then it's equal sharing, and there is no difference, which makes sense, right? It's basically, you can think about this like a little tug of war between the electrons. So who gets to win the tug of war and pull the electrons closer towards them? Well, if they're the same element, that's like if I said I played arm wrestle or played tug of war with myself, and I won. It doesn't make sense. It's a circular argument, and you sound like a crazy person, right? Then this difference here where it says 0.1 to 0.4, it's still non-polar, but it's not pure. There's some difference between them. Now that might make you think that you do need to know the amounts and measure it. Well, if we go back, you really don't, because if you look, notice here from boron all the way over, every difference is 0.5. So any of these elements that are making bonds, the difference is going to be 0.5. And then critical is hydrogen's 2.1 and carbon's 2.4. So basically what this tells us is that carbon hydrogen is that 0.4 and it's nonpolar. And anything that isn't the same element, carbon, carbon, or fluorine, fluorine, etc., and isn't a carbon hydrogen bond is polar. And that difference would be 0.5 and up. And it goes to 1.9, but that's really just the hydrogen fluorine extreme example. So again, basically the same element or a carbon hydrogen bond, that's going to be nonpolar, and then anything else is going to be a polar bond. Right, and anything beyond the HF bond then is ionic, and we don't really care about measuring the difference between it. So a couple of examples, right? Chlorine bonded to itself. You can't win an arm wrestling match or tug of war with yourself. And then here we've got hydrogen, the least electronegative. Chlorine's right below it, right below fluorine, so it's got to be electronegative. And here it's measuring the difference, but we don't really need to measure it, right? It's not a carbon hydrogen bond, and it's not bonded to itself, so it must be polar. And then here we don't really need to measure it. It's a metal and a non-metal. We can tell by the position on the periodic table. We don't really care what the actual difference in it is. We know that one's a metal and a non-metal. The electron completely transfers. That's table salt. This table here is, this chart here is just plotting it. So the percent versus the electronegativity. And this is what I mean is, here's this one extreme of hydrogen, the least electronegative, and fluorine, the most. And everything else up in this area is all the ionic compounds. So HF is this one little weirdo exception of the two strongest and weakest electronegativities. Every other covalent bond is down in here. Right, so this is again why covalent things are solid, liquid, gas, behave much differently than all the ionic compounds. With, of course, the one exception of HF. Okay, so when we have this polarity, it's called a dipole. The way people talk about it is they'll say, the molecule is polar, but if you're talking about the individual bond or the individual molecule, then it gets reverted back to this term and calling it a dipole. So again, a positive and a negative end. We won't be measuring it. Like, this is just a flash, a little foreshadowing. Only chem majors are going to see this. Debye's, again, not a history test. Same with Coulomb. You don't need to know their last names. You might see the terms again, but no one should be testing you on names, right? It's not a history class. Oops. The percent ionic character, you won't see it again after this. We already saw it plotted out there, and then this table is going to show us some examples where they have the dipole moment. You just need to know that that's what it is, right? And then obviously if it's the same element, 0, then almost every bond is going to be over that 0.4. And you can compare these, but a little beyond the scope of ours. Really what we want to identify is things that are nonpolar, so carbon hydrogen bonds, and then any element bonded with itself, which we'll see a lot of carbon carbon. And then basically every other bond is polar, right? And then a metal and a non-metal is ionic. So it simplifies things if we present it that way. All right, so is water a polar molecule? Again, this is how a microwave works. And one of the ways that they try to show that, convince you of that, besides the belief that a microwave isn't magic, what we have here is on the left is water, where they put a blue dye in it, right? Water is not normally this blue. If you've ever been, it doesn't happen too often here in Hawaii, but when the weather's really dry, if you've been in the desert, right, if you rub your feet on some carpet, you can build up static charge. And they've basically done that here with this glass rod. Then when the water comes flowing out, it's actually attracted to the glass rod. On the right here is, they used hexane, but it's basically gasoline, which is all carbon-carbon and carbon-hydrogen bonds. So the water has polar bonds and it's attracted to the glass rod. And that's how a microwave works. It flips the plates and oscillates the magnetic field, and the water molecules flip back and forth, and you get vibration and it warms up the food. With things that are non-polar, like gasoline, all carbon-carbon, carbon-hydrogen bonds, there's no attraction and there's no charge in the molecule, so it doesn't care about a charged. It has no reaction effect on some charged glass rod. And again, don't do it. But if you put gasoline in a microwave, it's not really going to do much. All right, so let's take a look at a few examples and determine what's going on. So this one is NO. Well, you can look up the electronegativities, but it was all 0.5 between one another on that top row. Is it a carbon-carbon bond? No. Are they the same element? No. Is it a carbon-hydrogen bond? No. So it must be polar. We don't really need to go to the table and look at it and do the math. So it's not ionic, it's not a metal and a non-metal. It's definitely covalent, but it's not a carbon-carbon, carbon-hydrogen, or the same element. So regardless of what the value is, we know it's a covalent and polar bond. All right, so we can put these Lewis structures together and look at how those valence electrons go throughout the whole molecule, and then understand the bonds. And this will tell us the three-dimensional shape, what the molecules look like. And then the polarity then will tell us how the molecules are going to behave and interact with other molecules. All right, the bottom picture here, this is a great thing to just memorize, or print this out and put up on your wall or something. This is the world of organic chemistry, right? So boron has 3 electrons, and it's kind of a strange element, so we won't use it much. But carbon has 4 electrons, so it needs 4 more, so it wants to make 4 bonds. You move over to nitrogen, it's got a 5th electron, so it wants to make 1 less bond. You move over to oxygen, it's got 1 more electron, so it only wants to make 1 less bond. Same thing now that you see the trend with fluorine. It's got 1 more electron, it makes 1 less bond. Carbon, 4 bonds, and then these electrons that are by themselves like this are called lone pairs. So carbon wants to make 4 bonds and no lone pairs. Nitrogen, 3 and 1. Oxygen, 2 and 2. Hydrogen is an exception, right? It only has the 1 s orbital, so it's only going to make 1 bond. But the halogens, they'll have 3 lone pairs around it. Hydrogen can't have any lone pairs. It only has 2 electrons, and that goes into making the bond. So these are these common bonding patterns that are basically just worth memorizing, right? This is going to be the basis of organic chemistry, right? The one more complex thing that's not shown here is, remember our multiple bonds, our double and triple bonds. So carbon wants to make 3 bonds, but it doesn't care if it's a single and a triple, or 2 singles and a double, or say 2 double bonds, right? As long as it has 8 electrons and 4 bonds around it, it'll be happy. All right, so let's start drawing these and do an example. This is nitric acid, HNO3. So the way, look at this, the way you put this together is you want the least electronegative atom. The one with the highest bond connectivity is generally your central atom. Hydrogen only makes 1 bond, so it's always on the outside. Then just start counting those valence electrons and start putting them in and connecting them. So nitrogen's 5, hydrogen's 1. There were 3 oxygens, there's 6. This gives us a total of 24 electrons, right? 18 plus 1 plus 5. All right, let's connect them all first, right? The nitrogen in the middle. So single bonds that get them all connected, that used 8 electrons. We got 16 left over. Start putting in the electrons as lone pairs. So we put 6 around each. These 2 oxygens, the other oxygen, because the hydrogen only needed 2 lone pairs. So we used 6, and 6 is 12, plus 4 is 16. So we used up all the electrons. So, whoops, I forgot the animation there. The hydrogen was already fine. All right, so then what's our problem with that last structure to here? Is what we needed to do is take the one set of lone pairs. They picked this pair. It doesn't matter which, the electrons are all identical. This nitrogen in the middle only has 6 electrons around it, right? The 3 single bonds. And then each of these 2 oxygens have 8, but the problem is they have 1 bond and 3 lone pairs. And what oxygen usually wants is 2 bonds and 2 lone pairs. So if we take that lone pair and we push it in here in between the nitrogen and the oxygen, now everything has happy octets. The nitrogen has 8 electrons around it. Both oxygens have 8. And it's happier than it was before. Now, this isn't perfect, right? The nitrogen normally wants 3 bonds and a lone pair, and this oxygen normally wants 2 lone pairs and 2 bonds, but we're pretty close to ideal. So it doesn't always have to be perfect, but it's got to be pretty close, and it definitely has to have the 8 electrons around it. Okay, I think we're out of time. Yeah. I don't know why it won't escape from the, there it goes. Okay, so we're out of time. We'll pick up here. You can see this stuff takes practice to do. You need to draw it out, and when you go and take OChem, you'll have, most likely the test will be in person, where you'll draw on a piece of paper and the instructor will grade your writing, your drawing it out. So the animation and stuff in here, it does it for you, and it's sort of like like watching someone dribble a basketball or hit a golf ball. You need to go and try it and do it yourself. So just like math problems where you pick up the calculator and you do the math, it's going to be the same thing here. And these are good examples. This one showed you step by step. Then these ones just go from the right, from the formula to the Lewis dot. They don't solve it step by step. So this one here, the HNO3, is really good for walking you through how to do it. And you apply this same, 1, 2, 3, 4, 5, 6 methodology to coming up with the Lewis structure for each one of these. All right, yeah, I'm over time. So we're done, obviously, for the day. And have a good weekend, and we'll pick up here on Monday. And I hit the unmute button, so if you want to hang out and ask questions, feel free to do so. And also, obviously, feel free to go.
Professor?
Yeah.
So I just have a quick question. It's regarding the exam, the third exam. So it's gonna be on the 20, like by the end of April, right?
Yeah, I think the 19th, which is
Okay.
2 weeks
The-
from today. Yeah.
All right. Okay. And then one more thing is, like, let's say, for instance, I got like the lowest score for the third exam, and then I did well on the final exam. So does it matter? Like for this three exams or midterm exams, it doesn't matter if I get um
Well, I dropped the lowest score of the 3 midterms.
okay, but the most important thing is we get better grades on the final exam, right?
Yeah, I mean, the final's worth twice as many points, so you wouldn't want to drop. I'm not going to drop the final because it's worth it. You'll certainly get a better score, total score, on the final than you would on each of the midterms. So,
Okay, because I'm just like thinking like, what if I failed on the final exam and then I get like good grades on the three midterm exams?
well, I mean, you don't know until it happens, but I would assume, the final is going to be cumulative where you can go back and study the old exams, and the problems are going to be somewhat similar in a review, and a few on the last chapter we cover, but most people tend to do better on the final, I
On
think,
the final.
because you're seeing the material again and you've seen an exam from me again, and it's not as much new material. So, I mean, if you've been, studying and working on it all semester, then it's not.
Okay, got it.
It's more that you have other finals. It's not that there's a great amount of new material.
All right, perfect. Okay, that will be all. Thank you.
Okay, see
See
you
you next
Monday.
week. Okay,
Bye.
bye-bye.